So how's your weekend?
It was pretty good. It was filled with a lot of studying,
What
you
were you
know,
studying mostly?
uh calculus and chemistry. I have an exam today for that, and I had a quiz yesterday for calculus, so I was
How do
just
you do?
catching up on notes.
How do you think you did on the calculus quiz?
I I got an 88 on that one. Um I missed 3 points. One, I'm not really sure why I missed. I could tell you the problem, and then I could tell you. So it was like it was just this one problem, and all of the problems, they come from the homework, just in like different numbers, or a different example or situation, but pretty much the process is the same. So I knew this what the problem was, and like I followed the same steps that I'd normally take to solve it. Only the answer was like completely different. But one of them I missed because of a sign, and it just took off the whole point. But otherwise, it was all right. They just it was either solving or with limits, or just differentiating, or finding the equation of tangent lines to a curve.
Not too bad. So remember that I said that you're the only one taking this class right now, which is really kind of nice because it allows me the freedom to structure the class around what I feel like your needs are. We don't have to worry about covering things if you already know what they are pretty well, and we can spend extra time on the things you want to have extra time spent on, which is
Hmm.
really nice. So if you want to go over any of the problems from the quiz, if you wanted to ask any questions about them, we could do that. Otherwise, I think we're just going to dive right into the topic that I feel like we should discuss today. What do you think of that?
That sounds good. If you'd be willing to, I'd love to go over the at least like one, because I only missed three.
All right. So what we're going to do is I'm going to allow you to write on the board. Oh, I think you already have permission. So go ahead and see if you can write the problem on the board. You can type it if you want, or you can use the pen tool if you prefer.
Well, how do I write?
Do you see the toolbar up above?
You see annotate? Is that
Yeah.
it?
Yep. Exactly. You want to click annotate, and then it should give you the. Yep. Exactly.
Oh,
You got the hang
wow.
of it.
Okay. Okay. So let me go to the problem. Yeah, it was yesterday. It's the quiz. Oh, I have to go here. Um, okay, so the question is, estimate the price of 1 barrel of crude oil on January 25th, 2016, and the rate at which the price was rising that day. Um,
Could you write
so
it? Could you write all the information on the screen for us?
yeah, so I'm gonna do my best to draw a little graph here.
Here, I'll start with the axis.
Okay.
So, all right.
Could you
So,
move the y-axis a little lower?
oh yeah,
Because all we need here is let me go to it.
like
All we need is the first quadrant.
okay, cool. All right.
Okay,
All
so
yours. It was a long weekend, wasn't it? I think the last time we had class was over a week ago, last Tuesday, right?
yeah,
We had
due to President's Day.
exactly. Our weekend included another whole half of a week, which was really nice. Why can't it do that all the time, right?
Yeah, it'd definitely be nice. So that
I dare say I might actually get a healthy amount of sleep if that were to happen.
chance would be a fine thing.
Indeed.
Okay, well, I mean, so you understand. So the x-axis it's increasing by 5, and it represents days in January.
Perfect. And then what about the y-axis?
Y-axis is going to be dollars, starting from 23 going up. It's price per barrel, sorry.
So 23 would be our first value.
Yeah, and it increases by 1.
Oh, by
So
one, okay.
price per barrel.
I'm not going to write all the numbers. I'm going to do something like this, 23, 24.
Really, all we need is 26.
All right, I think we're in good shape.
Okay, so
Figured
the
if it's
graph
cheating.
looks something a little like this. It starts on 26, it dips, it's in between 15 and 20. So
Is it linear or is it a curve?
it's a curve. It's not gonna go below 25. So I need it's going to stop.
Here, if you want, I could just maybe make the line to indicate that it can't cross right there. And then I'll
Yeah.
erase this.
So it never goes below that line that you just made, and it looks a little like this. Give me 1 sec. I need okay, and then it rises right there, 20 and then 30. It's halfway. Okay. So right here would be about halfway in between the 26 and the 25. That's where I'm trying to indicate this curve stops. So it'd be about 25.50, I would say. But yeah, so the first part of the question is just to estimate the price of 1 barrel of crude oil on the 25th, which is right here. I said it was about 25.20, but it could have been 25 as well. And then it also asks, so the price of 1 barrel of crude oil was rising about how many dollars per day on the 25th. And so the way that I approached this was by taking so on the 25th, we have the 25th right here. And so what I did was I took this point and this point by the 20. So that would be about, we have 1 point is 30, 25, 50, I would say.
And is that the approximated price or is that the rate of change of the price?
No, this point right here just
that's
designates
point,
the
okay.
price of 1 barrel on the 30th of January. And then I take the second point on the 20th of January, which I would say was about $25. So we have 20 and 25. For precision, we'll do 0, 0. So here, so I chose this point and this point, and then by finding the slope of in between these 2 points, that I would assume that's what I did in the homework when I had this question on the homework. Who knows how long ago? That would have been a couple weeks, but so it had just been 25.50 minus 25 all over 30 minus 20. And so this gets you 0.5 over 10. Oh, what? I see. Okay, and then 0.05. Huh. Well, I seem to have just resolved it, but somehow I got 55. I'm not sure why.
You know what? Sometimes talking yourself through a problem is really all you need. Have you ever done any kind of programming, any coding before?
A little bit. I don't know if you're familiar with the website learncpp.com, but I'm attempting to learn C++ through that website. It has like a bunch of tutorials, and the only reason why it's free is because it has like ads covering any part of the page that isn't the actual tutorial.
I love C.
But otherwise, no.
It's a great language. I think I know most of the important things you need to know. The last CS class I took in Reno when I went to UNR was, I think, CS 302. We went into abstract data structures. We went to operator overloading. and dynamic memory allocation. Cool stuff. I love programming, but in programming, we have this method called rubber duck programming, where if we're stuck with a really complicated problem, we have a rubber duck that's sitting on the desk, just chilling there, and we explain to the duck everything we're doing. And then for most people, after a few minutes of the conversation, you get that moment, you're like, oh, that's what I did.
Yeah.
Sometimes it really helps just to talk yourself through the problem and understand what really happened.
Yeah, that's true. Then because when you say it out loud, you're actually saying it, and compared to when you're reading, you're more like you're scanning it.
You're making a better connection with it than you did before, just from speaking.
Yeah. So the range of answers was from 0.04 to 0.6, and somehow I think what I messed up was this part. I somehow
Did you swap them?
I might have because or I might have just I think I neglected this 5 right here because I got 5.5, and I could pull
Oh,
out my work from the day of, as a matter of fact, if I could find it, and I still have the work, but so this is what I got out of that, and then obviously divided by 10, that gives you 55, but I should have gotten here. I had ample time to check it, but I said, oh well, I followed the same steps, so I should be fine. And then there was only one other question.
is it all right if I erase this?
Yeah.
And by the way, I am recording this. If you want to just review any of the things we're doing today, it'll be on my YouTube channel.
Okay, sounds good. I believe I've subscribed to it. If not, I'll be doing that right
Thanks,
after this.
thanks for the subscription. Much appreciated.
Okay, so the last one, I got the first part right, and then the second one wrong. It's a marginal revenue problem, and
Is there a graph?
no, it gives us the function. Suppose the revenue from producing and selling X units of a product is given by the function R of X is equal to 10X minus 0.04 X squared dollars.
X squared values?
No, dollars.
Oh, dollars.
Or I mean, R of X would be in dollars once you calculate it. So it says find the marginal revenue at a production level of 15. To do that, all you have to do is find the derivative of the R of X function, and then solve for the derivative, solve for the R prime of X, where X is 15. I got $8.8 per unit. That was correct. The one I got wrong is the production levels. It asks what the production levels are when the revenue, or where the revenue is 400. And for that, all you have to do is substitute 400 in for R of X, and then it becomes a quadratic equation.
Do we want to substitute it in for R of X, or do we want to substitute it for R prime of X?
R of X.
How do we know for sure?
Well, it says the revenue is 400. We want to find the production levels. So this one, when we have the revenue, the X would be the production levels. And there are 2.
It seems weird that they would ask for this and not the derivative, considering this is a calculus class. So
I mean, they sort of ask for it. When they ask for the marginal revenue, the way to get to the marginal revenue is by finding the derivative of the original revenue function, and then you just solve that for when X is equal to 15, because they want the production level at 15, right? So the marginal revenue when they are producing 15 units.
that makes sense.
Um,
So do I have this part written right, this equation? Is it equal to 4?
Yes.
So I probably want to start
moving the 400.
400. So I probably want to start by moving the 400 to the other side. But before I do that, I'm going to multiply everything by a negative, just so we have a positive leading term. It's good to have a positive leading term. So we're going to have positive. Here, I'll type it. Positive 0.04 x squared. I'll put the squared later. And then we're going to have minus 10x. And then we're going to make the 400 negative, and then we're going to add that to both sides. So it'll be a plus 400.
Mm-hmm.
Now what we might want to do is multiply everything by 100. Yeah, and then we'll have 4x squared.
Okay. I just did it that way it was, but I mean, you know, it doesn't really matter.
And then you can use any method you want to factor it now that it's in this form. You can use the quadratic formula. You can complete the square. It's really up to you.
Here I used the quadratic formula. So it would just be 1000x plus or minus 1000 squared minus 4ac. So I mean minus 16 times 40,000 all over 8.
Let me see if I get something similar.
Yeah, so
So we have two x values that solve this. We have x is 50, and we have x is 200.
oh, okay. So that's what the correct answer was. I got 225 and 25 somehow.
Oh,
But I'm sure it was just an issue with my quadratic, like right there. I must have done something wrong at that time.
the vast majority of mistakes that people make in a calculus class is not actually related to the calculus part of it. It's related to the arithmetic and the algebra.
Yeah, yeah. That's
I remember when we got one of our first tests back when I took AP Calc in high school, the teacher was pretty upset. You could tell just by the look of blind fury on her face. And she says, what I've learned about all you guys is that you can do derivatives and integrals, but you can't add, you can't subtract, you can't divide, you can't multiply. And we were all just, I was deeply ashamed. I can't speak for anyone else, but yeah, no, that wasn't too good.
yeah, no, I mean, the simple mistakes, really, I mean, you know, at some level, I feel like, you know, I shouldn't be making them. I got one whole point off because the question was it was a question where they asked us to find the equation of a line tangent to a curve, and we had to put it in points form, and literally they gave the slope as well as a point, the point that the line was tangent to, as well as on the curve. And all you had to do was put it in point slope form. And I still, like, I don't know how, but I got one. I put a plus sign instead of a minus sign. And, you know, because of that one mistake, the computer that was grading my quiz took like the whole point away. So that was just, you know, it's like that could have been avoided, you know.
Are you using my math lab?
Yeah, yeah. Pearson or something like mymathlab.com is the website. I think it's made by Pearson though.
Yeah, exactly. I had that for a few different math classes that I took. I remember taking linear algebra. It's math 330, and it's notoriously tricky and technical. And we were using Pearson, MyLab, and Mastering. And if you make one little mistake, if you flip a minus sign, you get the entire problem wrong. And
Yep.
you can't show your work. But I have a really cool teacher who says, hey, if this happens to you, come in my office hours, and if you clearly know what you're doing, you'll get full credit. And I was really happy. I was happy to hear that, because these problems commonly took multiple pages for each problem, multiple pages for a single problem, and they get really ugly and nasty. So
Yeah. Yeah.
that took a little bit of the tension, the stress off my shoulders.
Yeah.
Yeah.
Especially like if like I was super nervous for this for the quiz. And then it was only 15 questions with 3 hours. So at one point I was like, you know, I stopped being so nervous. And then I was checking through my work. But you know, I guess I just gotta pay attention more, and then I should be fine.
So what do we want to do after that?
Well, that's it for me. I got everything else right, and in that one question, I know it was a simple sign error of signage. So, um, whatever. Let me see. So, I've just finished. That was chapter one. That was the chapter one quiz. So, chapter two is on the application of derivatives, and I actually found this very interesting. It was the chapter section 2.1 was on describing a graph or a curve. And yes, I really had some issues with one part. So it says that there are 6 key things about a graph. One is the increasing decreasing points, or something like that. There's asymptotes, inflection points, concavity, um relative minimum and maximum points, absolute maximum and minimum points, and just when the graph is going from increasing to decreasing. Let me see. Yeah, so increasing and decreasing functions. Extreme points is what those are called. Absolute maximum and minimum points. But my issue was, if I go back to this thing, the actual questions. So it would give me a graph, and it would ask where it's increasing, where it's decreasing, or where it's concave up, where it's concave down, based off of the labeled points on the graph. Would you like me to draw one?
Oh yeah, go for it.
Okay. So this one, boom. Okay, this should be easy to draw. So it goes like somewhat like this. And I have points labeled here. This is A. B is right next to A. C was about here. The D was at the top. This is pretty poorly drawn, so it might be hard to interpret accurately, but
Oh, it's better than most of the graphs I draw.
I don't know about that. Yeah, some pretty nice ones.
Thank you.
So yeah, so these are the ones. And so there are 3 questions. At which points is which labeled points is the function increasing? For this one, it says the correct answer was C and F. And when I go and look at the textbook, right? Where is it? It says that when you want to know if it's increasing or decreasing, in an interval, you have to look at so it says we say that f of x is increasing at x is equal to whatever point, right? So we could say C in this case because that's one of them, provided that f of x is increasing in some open interval on the x-axis that contains the point C. Um, so I really didn't understand what that meant. But for example, I would say that in this case, when I look at my actual graph, the tangent line for B on the actual homework problem is it's not the one that you'd see here, which looks like it's up. It's more like that. So this is just a bad drawing on my part. But
Supposed
I
to
did
be
this question multiple times, and like they would give me different graphs, and some of them were just like I didn't understand. So, but this makes sense. So if I draw the tangent line to C, that's sort of what it's like, and it's increasing, right? So if we look at it from left to right, it's going up. This one for F as well. This would be positive. Then it says at which labeled points is the graph concave up. Oh yeah, this is definitely one of them. So it says the correct answer was at A, B, and F. Uh, it took me a while to figure out why they were saying this, but I came to the conclusion that they were saying that it's concave up at these points because if you look at C, D, and F, this is where it's concave down because it's, you know, like that. So this is right here in the part it's concave down, but I couldn't understand this because I could look at A, B, and C, and I could say that these are all parts of a graph where it's concave up when it looks sort of like that, you know. And then the same for like E and F. They could, you know, it could look like that, where you have E here and F here. So I didn't really understand that at all. You know, I sort of just, you know, kept trying it until I got it. And then the graph has the most positive, and then it asks where the graph has the most positive slope. It says that you can use commas to separate your answers. So I chose C and F because those are the most positive ones. However, it actually only wanted one, I guess. So it was C. But yeah, this concave up stuff and this concave, these, you know, so where a graph is concave up and increasing and decreasing, those I don't know. I can't get those like consistently.
So let's go over that. So just in general, what does concavity mean? I know we had geometry. We probably have a pretty good idea of what concavity means in a geometric context, but what does concavity mean in a calculus context exactly? How would we describe that in terms of the way a graph works?
Um, I would just say like when it changes from increasing to decreasing and decreasing to increasing or vice versa, I would say that's what causes concavity, or that's
That's
what it
not
looks like.
that's not necessarily true. So I like to think of concavity in terms of the graphical part of this. So I like to think of a function as being concave up when the section of the graph looks like a smile. I consider a graph to be concave down, or sorry, I consider a part of a graph to be concave down when it looks like a frown. A frown.
Mhm.
So if we want to draw a region that kind of divides this part right here, see how we have a part that looks like a smile, we have a part that looks like a frown. We
Yeah.
want to pick a place where it's neither of those. We want to pick a place where it's neither smiling or frowning. So
Mhm.
I'm just going to pick a generic point right there. I'm going to call this point A. So we call point A point of inflection. And a point of inflection is a location where it changes from concave up to concave down. So I want to maybe draw a rectangle around this interval. So on this interval right here, it's concave down. And then on this interval right here, it's concave up. But on point A, it's neither concave up or concave down. Point A is
Mhm.
either concave up or concave down. That's where it changes from one to the other. And that's why that's a point of inflection. So a point of inflection occurs whenever a graph changes from concave up to concave down or from concave down to concave up. So in your graph, it looks like C would actually be a point of inflection. And then D would also be a point of inflection. And then we have A and B would be concave up, and then also F would be concave up as well. And then D would be the only one that's concave down.
So point of inflections, they cannot be either.
Exactly. If that would be,
Uh,
what is concavity exactly in terms of um, the algebraic way of doing things? Like, how do we find concavity if we weren't given a graph and we're given a function instead? What if we're given some equation? How do we find, for example, the concavity of something maybe like this without a graph?
um, well, I'm assuming that we would have to like pick a bunch of X points and then find the intervals or create inequalities for when X is increasing at until a certain point and then it starts decreasing again and so on. That's my only idea.
So the best way to do this would actually be by taking the second derivative. So when we take the first derivative, we can use that information to find where the function is increasing and decreasing. So we can tell that it would be decreasing until we get to this point right here. So this black rectangle represents function behavior that's decreasing. If I make another rectangle right here, this shows function behavior that's strictly increasing. So the derivative is positive here. The derivative is negative in this rectangle. So we're going to do something very, very similar to find concavity intervals. So we're actually going to take the second derivative, but it works the same exact way.
Yeah,
And
yeah,
I'm going to draw a more specific graph. Is it all right if I erase what we have here?
yeah, yeah.
Just a quick second. I want to pull something up. I want to draw it on decimals to make sure it has the behavior that I wanted to have before I draw it. I think a cubic would be good for this example, maybe. So we're looking for intervals of concavity. All right, I think I found a good one. So let's say we are given this function. Let's say we have y is equal to x to the third power. I'm going to write the third power a little later though. Minus 3x squared. Write the exponent later, and then we have a plus 4. And we're interested in finding the intervals where this function is concave up and where it's concave down. And they gave us a nice little graph to use. So I think I'm just going to draw the graph. So we have a local maximum occurring at x is 0, and that would be the point 0, 4. We have a relative minimum occurring at the point 2, 0. So right here, and this is going to be embarrassing. I'm going to try my best to draw it. If you have to laugh, just do so quietly.
Not at all.
And I think that's it, yeah. So we can tell graphically where the information lies, but let's do it with using calculus instead. Let's take the second derivative and get the same information that way. So we have y. We're going to take the derivative. We get y prime is equal to 3x squared minus 6x. And then see if you can take the second derivative for us. Just take the derivative of the derivative. You get y.
So it would be 6x minus 6.
Wonderful. So we want to set this equal to 0. And the reason why we want to set it equal to 0 is because if we do that, it will tell us the points of inflection, because concavity is 0 right here. It's not positive or negative, it's 0. And then same thing occurs. Actually, I think that might be the only point of inflection. I think so. Yeah, it looks like it. So setting the second derivative equal to 0 is how we find our point of inflection. So what I want to do is I want to add a 6 to both sides and then divide everything by 6, giving us x is equal to 1. So now we want to talk about exactly what to do with this information and what it means graphically as well as algebraically. So what we want to do now is we want to make what's called a sign chart. So I'm going to take the single critical value. That's what we call it when it exhibits behavior like this. The x equals 1 is a critical point or a critical value. So I'm going to put that right there. So what I want to do is I want to plug in a test value that is less than 1. It could be anything. I'm going to pick 0 because it's nice and easy to work with. So my goal now is to find y prime of 0. Or sorry, y double prime of 0. Plugging in 0 into the second derivative, 6 times 0 minus 6, we get a negative 6. So the thing about this is we don't care exactly what the value is. The only thing we really care about is if it's positive or negative. So we can tell that when we plug 0 into the second derivative, we get negative value. So the way I annotate that would be kind of like this. I just maybe make a minus sign right there. And then we want to do the same thing with the value that is greater than 1. I'm just going to pick 2. So I want to find y double prime of positive 2. Plugging it in, we're going to get 12 minus 6. We get a positive 6. And again, we don't care about the exact value. We only care about determining whether it's positive or negative. So we have a positive value right there. Whoa, what happened?
Wait a minute. So when you plug in 0 for x, right?
Yeah, into the second derivative.
So you have 6x is minus 6 is equal to 0.
Yes.
And then you isolate x and then you get 1, right?
Yes. No.
So how do you get this negative 6 when you if
So this is the second derivative, right? Y double prime is 6x minus 6.
mm-hmm.
So y double prime a 0 occurs when we plug in a 0 for x. So instead of 6x, we're going to have a 6 times 0. And then what do we get when we simplify?
I see. Yeah, sorry. The negative 6, you're left with negative 6. Okay. I had a brain fart, sorry.
No worries. It's all good. Happens to everyone. You should see me try to teach a class without caffeine. It's not pretty. So caffeine is just kind of my job security. I can't teach without it. So we found concavity at 0. We found out that when x is 0, the concavity is negative. And we found out that when x is 2, the concavity is positive. So whenever we have just one single point where it switches from one type to the other, we call that a point of inflection. And notice how it looks. I mean, this is merely by coincidence, but it looks really, really good. It makes sense that this point right here is the point of inflection because it's not concave up or concave down at that point, which means that we could make some line right here. And we can clearly see that everything to the left of the line would be concave down and that everything to the right of the line would be concave up. So that's concavity in a nutshell. That's how we find it graphically. And that's how we find it using the derivative, the second derivative.
So the second derivative is not a definition of the slope of a tangent line at a point on a curve. It's the second derivative is like it defines inflection points. Is that what its purpose is?
Well, not just inflection points, it determines concavity. So the first derivative determines increasing and increasing behavior, rates of change, and then the second derivative is what indicates concavity.
But so is that its like main use?
Yeah, exactly. This is probably the only reason why we have to learn the second derivative and how to use it.
Well, I mean, it's very easy. It's a very simple concept. I like it because of how easy it is. So I'm not gonna complain if this is all I have to do.
Yeah, not too bad. So anything else you want to ask about? Like I said, take advantage of you being the only guy in the class to ask whatever you want.
There was one more type of question that I did not understand. Basically, it was just a graph where if we say this is our thing, they had it to where like it was like this and then like that. And then it would say, so if we say that the x right here is 5, it would say, what is the graph? Or is this how I should make? Oh, give me one sec. I'm not doing a good job of explaining it.
Here, let me make the axes for us.
Yeah, let's just erase our, yeah.
So what else do they give us information-wise?
Not much. It's just a graph and it asks where it's increasing and decreasing, but they were really finicky about this. Where is it?
Here, let's move it over a bit. So do they give you an equation or do they only give you the graph?
Only the graph. Okay, I found it. So could you make this like a more like a plus sign so that I could use the left and right of the y-axis?
Oh, yeah. No problem. You mean like that?
Yeah, okay. So I'm gonna erase this stuff because it's not right. Is it erasing?
Here, I'll help.
Okay, there. I don't know. I was clicking on it, but it wouldn't work. So it's gonna start from right there. So essentially, okay, the graph starts like so, and then like that. And these go on. So we have this point right here. This is 1. X is equal to 1, right? I'm not sure about the y. It's in between 1 and 2. But so it says for x, so when x is less than 1, so everything to the left, which of the following statements is true? And it gives us the statement, the slope first increases and then decreases. The slope of the graph is increasing from left to right, or the slope of the graph is decreasing from left to right. So my issue here is that the correct answer was the slope of the graph is decreasing from left to right. However, if this is how we're supposed to read the graph from left to right, this graph is increasing as it goes up, and then it decreases. But from down here to x to from whatever x this is to 1, the graph is mostly just increasing. So um I guess the only way to say that it's actually decreasing is when you look at it from right to left. So that was my question, and I couldn't get this right. I was like, whatever I thought, it was actually the opposite, and that's, I had to turn it in by 10 p.m. But I didn't understand why they would say that it's decreasing from left to right, because I mean, looking at it, it has a positive slope. If you were to take, just the slope of any point from, the top right here to here.
You're absolutely right. So it's weird that they would have you go from right to left instead of left to right. That's really, I don't see that too often.
Yeah, no, see, yeah, and then but they even said from left to right, and then I'm just looking at it, and like, left to right, it looks like it's increasing.
Yeah, you're right. I think it's just maybe they made a mistake on the test, but you did it right.
Okay.
Anything else?
No, I mean, that's it for me.
All right. So I think we should maybe dive into maybe review continuity a little bit. So
Yes.
what is your understanding of continuity of a function? What does continuity mean?
Continuity means that for any x, you have a y.
Perfect. Exactly right. Can you give me an example of a function that's continuous for all x values?
Yes. So I'll do this.
If you want to graph it, that's fine, but I also want to have like an equation.
Oh, well, I'll just do y is equal to x. Yeah.
That works. Now, can you give me an example of another function that is not continuous for all x values?
Yes. So I'm gonna make this a piecewise function. I think that's how you do it.
If you
So
want to do a piecewise, that's fine, but it doesn't have to be a piecewise. For example,
no.
we could just do natural log of x, right? Natural log of x looks like this, and it stops
Oh yeah.
vertical
Yeah.
axis.
That's
So
true.
this is not continuous for all x values.
So ln of x, that would be the y is equal to ln of x. That
Mhm.
would be the excuse me, the written.
Mhm.
Okay. Okay.
This is not continuous for all x values.
Yes, because there's an asymptote and it doesn't, yeah.
Exactly. So I feel like you have a pretty good understanding of that. What about differentiability? What is your understanding of differentiability?
Ooh, I remember reviewing this. Well, when you differentiate, you take the derivative. So when something is differentiable, when a graph is differentiable, I'm assuming that it's continuous at that point. Uh, and you can find the slope of the tangent line at the point. I would say that that's what differentiability is.
Exactly. So I want to see if you can draw for me an example of a graph that is not differentiable at every single point. We want to just have a good understanding of what it means graphically to be for something to be not differentiable at a point.
Okay. I'm pretty sure that would look something like this. So it'll be y of x, y is equal to x up until whatever this x point is, and then it'll go like that. And this would not be differentiable at this point, I think, because of how you make the tangent line or something.
Exactly. We call this a cusp. A cusp is just a corner.
Yeah.
It's a sharp part of the graph that does not have a derivative.
But I mean, so what if I draw a tangent line? I mean, if this is the mathematical, could this be considered a tangent line? Or no?
It wouldn't really work because if we want to approach it as a limit, what happens if we, here, hang on just a second. I want to split it up. So we're going to have this part of the graph, And then we're going to have this part of the graph. So what happens if we travel from left to our point right here? What is the derivative going to be? Is it going to be a constant derivative on interval A?
Yes, because it's a straight line, right?
Exactly.
Yeah.
And what about interval B? Does that also have a consistent derivative, a consistent rate of change?
Yes, this one, it's a horizontal line. So I think the slope of a horizontal line is always 0.
Exactly. So my point is that if we travel from this side, our rate of change would look like that. If we travel in the other direction, the rate of change would look like this. So this line right here, this one is not, it's not the rate of change, it's not the correct rate of change for either interval A or B. So you have to approach it as a limit. If you take the limit as x approaches this point from below, you would have one rate of change. If you take the limit as x approaches this point from above, you're going to have this rate of change. So there are going to be two rates of change, and none of them occur at this point. So this does not have a derivative. You know how kind of like when we have something like this, we say that this function is undefined when x equals 0?
Yeah.
So what happens at this point is that the derivative is undefined when x is equal to 0. Mm-hmm. So this point right here has no derivative whatsoever. It's not 0, it's not positive or negative, it's undefined.
And that's because and now it's basically because you have one rate of change on one side and then a different one on the other, right?
Exactly. So there's another situation in which this occurs. Do you know what that might be?
Another one.
Another where it's not differentiable.
I think I've seen ones like a graph where it goes like this, and then you have like an open circle, and then here too. Would that be like another one or?
Exactly. So we can see that this is discontinuous, right?
Yeah.
Everything that's discontinuous is automatically not differentiable. So if you see something like this, and you can tell right away that it's not continuous, it's also not differentiable automatically by default.
Okay. So differentiability depends on continuity?
It absolutely does, yes.
Okay.
So another example I was thinking of is I want to use natural log of x again.
Okay.
I'm going to draw the curve as best as I can. And then what happens if we take the limit as x approaches 0 from above? Or do we approach a certain value?
Wait, so what happens if we take the limit of x is 0 from above? What would above mean? From right to left?
Oh, above would be from, right to left, exactly.
Right to left. Okay, so as x.
So we can tell that we're decreasing, right? If we draw a tangent line right there, it's decreasing.
Yeah, when reading it from right to left.
It's also decreasing there, but by a different amount.
Yeah.
So if we were to go all the way to 0, we would have a vertical tangent line. It would just be straight up and down. And remember from algebra 2, it just doesn't make sense to have a graph with a vertical tangent line. It's impossible to find the derivative.
It's undefined.
Exactly. Yeah. So the derivative, it's not differentiable when x is 0, because not only because it's not continuous, but because it would represent a vertical tangent line, and that would indicate an undefined derivative.
And wait, this is only for the natural log of x, or
it could apply to different functions as well. For example, what if we have cosecant of x? I want to draw that one real quick.
Cosecant of x. I'm assuming that this is one where the asymptote is at 0.
Well, it's the inverse of sine of x. So sine of x has a point right there. Cosecant of x looks like that.
Yeah. Okay. So.
Yeah, and it has the same period as the sine function. It has a period of 2 pi.
I really need to review this.
So if we were to start at this point right here and work our way to the right, eventually we would have a vertical tangent line. So sine of x is differentiable on every single value of x, but its inverse, cosecant of x, is not differentiable on every value of x. And the reason why is because we have a lot of horizontal tangent lines in the domain. So this green line is sorry, I said horizontal, I meant to say vertical. So this green line it indicates a location where it's not differentiable because we have a vertical tangent line.
Wait, but I mean, would the tangent line of, like, let's say this line keeps going, right? Would the tangent line though, would it really be vertical? Because an asymptote and this function right here, this one would just, it would constantly, so the y would increase and the x would also increase, but it would increase by a smaller amount each time. So would it really be vertical? Or, I mean, because I mean, I'm pretty sure it would be like very, very, very slightly like not vertical, like slanted, I mean, but like only by the slightest degree.
Yeah,
That was my understanding.
yeah, I see what you mean. So we're not talking in exactness here, I guess, for lack of a better word. We're talking about theoreticals. We're talking about theoretically, if this were to touch this, we would have a vertical tangent line. If theoretically we would reach this green line, it would be a vertical tangent line. It's kind of like how if we take the limit as 1 over x, limit of 1 over x as x approaches infinity. So
Mhm.
do we agree that this function would never really approach 0, no matter how big our x value is, whether it's 10 or 100 or 1,000 or 500 billion trillion?
Yeah.
So that's why we have to use a limit. So we use a limit to determine that theoretically, if x could reach infinity,
Oh, so
theoretically,
okay.
yeah, and then
Yeah, so we're using limits. Okay.
so theoretically, if this thing could reach the curve, or if it could touch the tangent line, it would be a vertical slope, and it would have an undefined
Uh-huh.
primitive.
Oh, yes. Okay, and that's why it never actually touches, because a graph can't be undefined, right? Or the
Exactly.
slope of it. Okay. Yeah, that makes sense.
So that's continuity. That's differentiability. Any questions?
No, that was a much better explanation, honestly, than the book.
I'm really happy to hear that. So,
I
is
mean, it's like you said, you show me the actual geometry behind it, or
yeah,
what it
exactly.
really means and looks like, not just words.
It's like I keep saying, human memory is flawed. If you remember the steps, you won't really have a good idea of how these things actually work unless you can picture in your mind what it really represents, draw the picture yourself, and then you have a much better understanding than you would otherwise. So it's good just to understand the core concepts instead of the steps. Kind of like long division. Like everyone knows how to do long division. They know it works, but they don't know why it works. They say, hey, we just multiply, we divide, and then we multiply, and then we subtract, and we do all these steps. But when we ask them why they do that, they can't explain that. And I also teach at Mathnasium. We teach long division much differently. We teach them to understand the core concept behind why it is the way it is. And then same thing for multiplication. You know, so many people can't tell you why when you do a multiplication problem like this, you put the 0 right there. I mean, sure, they know why, they know to put the 0 there, but they can't explain to you why they do it. So in Mathnasium, we teach them why we have to do these things. We teach them the core concepts so that they have a perfect understanding why things are the way they are. And I feel like the schools probably would, but unfortunately, they're not given enough resources by the government. They don't have support from their government or the financial backing to create a learning plan that helps each student understand things as best as they can. But that's enough of my tangent. I think we should not divert too far from what we're trying to do here. Sorry,
No, yeah, yeah, yeah.
I'm a big geek about this kind of thing. I can geek out about math all day long and different learning methods. I love it. So I want to create what you might consider to be an interesting challenge. I definitely think it's interesting. I want to give you a piecewise function.
Okay.
Let's say we have our first function would be x squared. And then let's say we have mx plus b. Mx plus b is only defined on the interval where x is greater than or equal to 1.
So x squared is for all x less than 1.
Mhm.
Okay.
Or actually, I think I'll make it all x less than or equal to 1. So actually, you know what? Yeah. Here, I'll make this one less than or equal to. I'll make the other one just strictly greater than.
Okay. Okay.
So my question to you is, how do you find values for M and B so that it's not only continuous, but it's also differentiable at every single point from 0 onward?
How do you find
So my advice to you
values?
would be to ignore the algebra first. So ignore all of this stuff. Can you draw a picture of a function of what a line would look like that's continuous and differentiable on the entire domain? Just draw what you think that would look like before we even dive into that algebra.
Well, I'm not too sure about B or the y-intercept, but if we were to make a straight line from this point right here, so this is for all x. So I would say that there would be a line and it would look something like this. That's kind of bad, but the slope of this line, the m of this line, would be equal to the m of the curve of this graph at this point.
Exactly.
So
Perfect.
these two slopes have to be equal, but the b I'm not too sure about. The b could be 0 because the blue function, the blue curve touches at 0 on the y-axis, but I know that for a fact that the two slopes would have to be equal.
I thought this would be challenging for you, but apparently it's way too easy. What is the slope at this point? Let's just start with that. How do we find the slope at this point? We know that it's a curve, so the slope right here would be different than it is right here, and so on and so forth. So how do we find the instantaneous rate of change at that point when x is 1?
First we take the derivative of the function, so it would be 2x, and then we solve for f prime of 1. So I think it would be 2,
You're
the
right.
slope. Okay.
So we have our first piece of critical information. So
Mhm,
n is 2. This is going to be 2x plus b. Now we need
mhm.
a strategy that would help us find b. Can you think of anything that would help?
Well, considering we know the slope of the line, the bottom function, we could like use a dotted line to extend it, and then all the way until we like, or use the slope to calculate the y-intercept. We know that it touches at a point where the x coordinate is 1, so we could maybe plug in um we have 2 for m, 1 for x, so 2 plus b. I guess I'm not too sure.
So we have a point right here that's 1, 1. And the reason why we want to use this point is because it's the only point that's common between both of these pieces of the piecewise function. It's the
Mhm.
only point they have in common. So we want to use that. We have x is
Oh,
1. We have y is 1. So what I'm going to do is I'm going to
yeah.
do 2x plus b. I'm going to set that. I'm going to make it y equals 2x plus b. And what happens now is we have a y here. I think I might just use capital B. That looks way too much like a 6 for my company. So
Okay.
we have
Okay.
y, which is 1. We have an x,
Yes.
which is also a 1, which means b is going to have to be, what's b going to have to be in this case?
It's gonna have to be -1.
Exactly. So 2x
Oh.
minus 1 would be the function for the
Oh.
part of this.
So
So
okay, so then that means that like if we extend this one, like with a dotted line, it would touch at wherever 1 is, -1.
theoretically,
Mhm.
but I'm so bad at drawing that it probably wouldn't be even close to that.
Yeah, no, same here. I don't think I could. But yes, but theoretically, that's what the B
Yeah,
means. So the B would always be the same. Okay. So that's how you find and then yeah, and then you just substitute for any x greater than 1.
right. So if m is 2 and b is 1, or b is -1, this would be completely continuous, completely differentiable. But if we tweak these even the smallest amount, it would just fall apart. It would no longer be differentiable.
Mhm. Mhm.
So yeah, like I said, I thought that would be challenging, but you just breezed right through it. So I think that's it for today. We're going to be having class again on Tuesday.
Okay.
I encourage you to come to class with questions next time. I mean, if you don't have anything to ask, that's fine, but write down a list of topics you might want to ask about. Maybe some things from class you're not too sure about. I'm happy to go over anything.
Okay. Well, I'll be finishing notes for math, and then I'm gonna plan on working ahead. And that way I I have questions for this class as well as more free time, and I can learn more and we can talk about more.
So you're an overachiever, is what you're saying.
When I really want to be and when I'm focused on it, yes. However, you know, if I get distracted, you know, it could be an hour before I get back on track.
Hey, can you share some of your motivation with me? I could really use some.
Motivation, begin with the end in mind.
Oh, thank you for that.
Yeah, just, you know, if you think about what you'll be doing once you're done, sometimes for me that just motivates me to want to be done faster. But I mean, at the same time, I still remember to actually make sure that I'm doing quality work or whatever. So
You summed it up really well.
thank you.
All right.
Thank you.
Well, hope you have a wonderful evening. I'll see you again on Tuesday.
Yes, sir. Thank you. You too.
Have a nice
Appreciate it. You too. See you next.